As he mentioned, my name is Brandon Fulk. I'm going to be giving a talk on putting the hype in Hypervisor. I'm going to be going through a bunch of different ways of doing binary coverage at a hypervisor level. So how many people here are in the security industry, whether it's web or binary? All right, how many people are in the binary security industry, where you're working with binaries and things not on the web? All right, so a lot of people are probably familiar with code coverage and what you can do with those things. But we're going to go through and talk about techniques on how to gather that information and how to try and use it to find more bugs and help your static analysts, do what they do. So first of all, a little bit about me. My name's Brandon Fulk, as I've mentioned like 5 times now. I've had a passion for OS dev for a very long time, so whenever I get an opportunity to do something very low level, I usually take it. So I started out with this OS, which is called Fulk OS. It started, 7, maybe even 8 years ago now. It was a collaboration between my mentor and I. And ever since then, I've been sneaking in little OSs every time I can. So I've obviously always been interested in breaking stuff. I've been liking security stuff. I've been into web hacking. That's kind of how I got it started out. I've been doing a lot of like game hacking, making cheats for games, making bots for games, all sorts of things of the like. So a little bit of an agenda of what we're going to be going through on this talk. First of all, I'm going to try and convince you why you should be listening to me in the first place, and that the stuff I'm actually going to be talking about is relevant. I'm going to be talking about code coverage, what it is by definition, and what it is by my definition as well. I'm going to talk about Fulkvisor, which is my hypervisor. We're going to try and go through that pretty quickly. I get excited about it, but it's mainly to teach you guys how I'm doing these things and what environment I'm doing them from. The bulk of this is going to be going through methods of gathering code coverage and using that code coverage. We're going to actually go through 11 different techniques on Intel and AMD processors that you can gather code coverage information. And then finally, I'm going to talk about what I currently do. After presenting all this information, I'm going to tell you what do I do personally after all of this time and fiddling around. So first of all, why am I here? So I put up this image of my hypervisor 3 months into development. It was all written in assembly at this point in time. But already 3 months into it, I had all these different configuration options for every different technique of gathering coverage and doing something with it in a different way, whether it be feeding back the actual coverage information or feeding back crashes. So coverage is starting to become pretty popular in the scene. How many people here have worked with AFL, the fuzzing tool? All right, a lot of people. So you're probably a little bit familiar with how coverage can help guide you with fuzzing and know what you have hit and what you haven't hit. So the thing with AFL is it requires you to build the source code, or build the source code with its custom compiler that puts in special hooks to keep track of what's been hit and what hasn't. But a lot of the targets I work on are all binary, and I can't get access to the source, and I can't build it. There are some ways with AFL to make it work with binaries, but they're a little bit crude, so we're going to be talking about ways around that. And then also, since I've done this as a hypervisor, I can also go after kernels and other hypervisors, which gives kind of a different perspective on the targets I can look at. So first of all, code coverage. This is kind of what I standardly look at for code coverage. I always have a log scale graph. It says either time in seconds or number of fuzz cases. And then on the y-axis, the number of edges I've hit, the number of blocks I've hit, whatever your metric is. So code coverage is pretty much anything that gives you information about the code you've hit. And that information can be used to help guide your fuzzers, as I've mentioned. And usually what you're looking for is some sort of way that you've hit unique code. Because unique code happens to be usually the cases where there are some bugs there because users aren't hitting it, they're not testing it, thus you're not getting crash reports back to figure out what's going on. So I go a little bit beyond just code coverage, and I just call it coverage. And I look at memory coverage, and register delta coverage. So memory coverage being keeping track of what offsets into buffers are being used, that could be stack or heap, and then the contents that's being read or written to from them to get a little bit more information than just the code that you've hit. It's possible that you can have bugs in the most common piece of your code, and it's hard to know that without tracking some other state besides just PCs. I also do register coverage, where I keep track of the state of certain registers. I keep track of kind of the mins and maxes. I keep track of the means and standard deviations and look for anything that's a huge anomaly. And then I'll also just keep a cache of the random, past 100 or 1,000 entries that I've seen in a register. I also do register delta coverage, which is the same thing as register coverage, except I'm not looking at the absolute value of the register. I'm looking at the change of the register from the previous instruction. So why would you want to actually gather this information? And we've kind of already hit on this, so we're going to go quickly through it. But basically, it comes down to you want to gather information of what code you've hit. It also means you can compare it with previous times you've run your fuzzer to see if changes you've made to your fuzzer have made it better or faster or find more bugs. So code coverage is a good mechanism because sometimes you're not always finding bugs. And if you're not finding bugs, how do you know if you're doing better than before? You need some sort of metric. So coverage information can also be used statically. You can keep track of all the code you've hit, and thus you can pass that on and color IDA if you want to, or you can pass it on to someone who's looking at the actual source in like a source line version. So I go through a few different coverage types. I'm going to be talking about these throughout the presentation. The main coverage types being PC, edge, chain, trace, memory, and register. So PC is probably what people are most familiar with. I just keep track of what PCs or EIP or RIP values I've seen. So basically each unique instruction I've seen execute on that system. And edge is any control flow transfer. So something gets called, a branch occurs. And now in some cases where PC coverage would just tell you one thing, you could have an indirect call or a jump where there are multiple destinations from one source, and now you track those as unique events. A chain is basically a glorified edge. There's just another control transfer in there. And then I also have trace, and trace is just the entire code flow. So you have every single edge that occurred such that you can reconstruct the entire flow of the program. And then memory and register coverage we kind of already covered, and just keeping track of memory state and register state. So now we're going to go a little bit into Fulkvisor. So I need to be a little bit careful because I get too excited about this stuff. But I've been doing Fulkvisor for about 1.5 years now, actually almost 2. I didn't realize it's been so long until I looked at some old content. But Fulkvisor is a hypervisor that's built for my own OS, which is called FulkOS. And since it's part of my own OS, I don't have to deal with Windows or Linux getting in the way. So I'm going to be doing a lot of things during this presentation where I'm having interrupts fire millions of times per second, and Linux and Windows just aren't too happy about that, so I kind of need to be able to control it all myself. So Fulkvisor was my first multi-threaded OS, so it was kind of cool and a big breakthrough for me as like an OS dev experience. It's been pretty cool so far. So Fulkvisor started out in version 1. I codenamed this Oreo. It's all written in 64-bit assembly because that's all I usually like to write stuff in. It's not the most convenient, as you probably know. But all it was capable of doing is I had a custom debugger written for Windows and Linux, and it would run on those respective targets. And I would load up whatever application I want under those custom debuggers. And when I hit a certain condition, I would save the state of the entire application I was looking at. That would be the memory state and the register state. Once that's been dumped out to a file, I can then load this up in my hypervisor and continue execution from wherever the snapshot occurred. Now, since I'm lifting userland applications, whenever a syscall is hit, I have to end the case. Unless I can somehow emulate the syscall if it's simple enough, which is what I first started doing. But since a lot of my work is on Windows, as a lot of you know, the syscall interface for Windows is gigantic and a little bit hard to follow, and it started to become a pretty big problem. This led me into Fulkvisor v2. It's what's called Brownie. It's still written in 64-bit assembly. The only difference is now for AMD. So there are a few big changes. First of all, this was actually a hypervisor. It was able to run Windows or Linux under it. So basically, you would PXE boot Fulkvisor. It would boot up whatever was on the disk transparently. And then you'd be able to take snapshots of whatever was running under there and load it up later to continue fuzzing. So it solves kind of the syscall problem from before, where syscalls that don't actually do any I/O, something that just enters the kernel, queries some information, and returns out, those would just go through without a problem. I still have a problem, and still to this day have a problem, of if anything does actual I/O where it's hitting MMIO space or other devices on the system, I have to actually terminate the fuzz case and continue. So it leads to this problem where I have to kind of snapshot around all of the I/O, but usually that works. Usually a file gets loaded, and then it's parsed, and then something else occurs, and I just focus on the parsing part. That leads us now to Fulkvisor v3, which is the most recent version. Since this all started out as a hobby, I wrote it in assembly just kind of for fun, but now it happens to be my full-time job, so I had to port it to C. So it's a little bit better now. I've got some cool features. I've got an ARM and a MIP simulator in there that are designed specifically for fuzzing. But there's really nothing too crazy in the current version that Brownie didn't have. So now we're going to start going through some of the dynamic coverage methods. There's 10 listed here, but there are 11 because the first line has 2. And basically, we're just going to go through all these methods one by one, define certain properties they have, characteristics, and how they can be used for code coverage. And, are they fast? Are they slow? Do they miss things? So on and so forth. So to do this, I've come up with these coverage method properties, these different categories where I try and figure out what all these things can do in some way or another. So the first one is countable. It's basically, can I figure out how many times I've hit each edge or how many times I've hit each PC. There are some that I'm going to be showing that don't have this property, where you only know whether or not you've hit it at all. You don't know how many times you've hit it. Register in memory basically is the method capable of grabbing register in memory information. Edge, chain, and trace basically says what level of depth can you capture with a certain method. Can you get an edge? Can you get a chain? Can you get a full trace? Convergence, so there are a few that actually don't give you the perfect result. So how long does it take to actually get to that perfect result if you were to run it long enough? The slowdown factor, how many times slower is it going to actually make your system run, because all of these have some expense to them. And then Intel and AMD, because I'm going to present some features that Intel has and AMD doesn't, and vice versa. So first we're going to go through single stepping. I'm sure everyone has done some sort of single stepping at some point in time. If you've ever single stepped an application in debugger, it's all using this on the actual hardware. And what it is you just set a trap flag in R flags, and this will make it so after every single instruction you execute, there will be a trap, which is essentially an interrupt into the kernel. And at that point, as a hypervisor, it breaks out and I can view whatever occurred. So I can see what instruction it is using some of the last branch record stuff, which on Intel and AMD tells you some of the previous branches that occurred on the system. I can figure out what the previous branches were, what the memory state is, so on and so forth. And if you single step forever throughout a program, you'll be able to figure out everything that it did. You can get all the register state, you can get all the branches. The downside is it's very slow. It has about a 350 times slowdown. Obviously, it depends on the target, but that's pretty unusable. You don't want to sit and wait 350 seconds for something that takes 1 second to actually execute. So next, to kind of solve this problem, Intel and AMD both added branch single stepping, which is the exact same thing as single stepping, but you set another bit in this debug control MSR, and it enables that instead of stepping for each instruction, you step for each branch. And this is a lot better because now you only have a slowdown of about, I guess the contrast is kind of weird, about 100 times slowdown. And the downsides are you lose the register and memory tracking that you previously had with single stepping, because now you're only breaking into the VM every single time there's a branch rather than every instruction. Next, there's something just that I call interrupt sampling. I think that's what the community also refers to it as. Basically, find any timer available on the system. There are many types of timers. And anytime they fire, you have an interrupt. Thus, you exit out of the VM. And now you're able to observe the system state and try and determine where you are, what registers are looking like, what memory looks like. But this is actually the first method that we're going through that doesn't give you perfect accuracy. You don't actually see every branch that occurs. You could maybe only sample 4 branches in an application that had 10,000 happen because you only had 4 interrupts fire. So it's kind of an interesting technique because you can change how frequently the interrupts occur. If you want more information, just turn up the interrupts, and if you want less information, just turn it down. So with this, you're able to get the edges by using LBR, which is the feature that allows you to see the last few branches. And on Intel, you can get a chain because Intel's LBR stack is about 16 entries. So you can see the previous 16 branches that occurred. So next, we're going to look at interrupt-based sampling. It's an AMD-only feature. It's practically identical to what I just mentioned, but it's a special feature that AMD has, so it's got its own timer. And what's neat about this is that it gives you some free decode information. It will tell you whether or not the instruction that you interrupted was a load or a store. It will tell you the virtual address and physical address of the load or store. So now you no longer need to actually decode the instruction and try and figure out what's occurring. So I'm not going to go on too much longer about this because it's pretty much the same as normal interrupt-based sampling, but you get some more special features out of it. So next, AMD introduced a feature called lightweight profiling, I think about like 6 or 7 years ago. And it allows you to do full traces of user space applications by basically setting up a buffer for it to record all branch activity, all instruction execute activity, or all decache miss activity. The reason that they did it userland only is because it's meant to be kind of guided for environments where you can't install a kernel driver, you're just on some system and you have to be able to trace an application. So it's pretty nice in that fact. Since you're only getting the actual traces, you're not able to see what registers or memory are being used because it's just all whizzing by in a trace. You could try and determine what's occurring by using those traces, but you're not going to see the exact values of registers. One of the downsides with this is that while the AMD spec technically says you could get full traces and full information out of this, when you go to set the count to 1, meaning give me an event every single 1 condition, it actually in hardware sets it to at a minimum 128. So you'll get one branch, you'll have 128 between, then you'll get the next branch, which means you're not able to actually construct the full chains or traces with this mechanism. But what is nice is that it is userland and is very quick due to the fact that it's not the full trace. But the downsides are, as a hypervisor, it's hard to inject userland memory. So usually I have to actually allocate the memory while I'm still taking a snapshot with the debugger that I'm using. So now we're going to talk about a fun little feature that happens to be undocumented on AMD for getting full traces. It will give you all of the branches that occur. It will give you all the interrupts that occur. It will give you any syscalls that occur. And also, I think it will give you SMM, but I've never actually observed it. But basically, you give it a big buffer somewhere in physical memory, and it will just use up that buffer and store each entry for each branch or control transfer that occurs. So it is very slow because there's no limiting on it. It will capture at all privilege levels, at all at all control transfers. So basically it writes out 12 bytes for every branch that occurs. And when you have a lot of cores on a system, now you're having hundreds of bytes being written for every branch, and now your memory is pretty much unusable because it's been saturated. It's also AMD only, as with the previous one. So I have some slides here going into the technical details of how it works. They're mainly here for reference because I will be giving out the slide decks. Basically, you disable it, you set up a base, you have it start running, and then you start processing the entries. So the key things here are there's this magic number here that you put in BH trace control, which is this MSR. I don't know why this magic value works, it just happens to. I found it in work by some CMU students that I'll actually reference in a couple slides. And I don't know why it works. I don't know what bits you can change in there. It'd be really cool to figure those out or obviously get specifications for it. So this is what an entry looks like in that. Basically, you're going to get a 64-bit virtual address for where the branch is going to go. You get a CS value for the code segment that is part of the branch. And then you'll also get this 16-bit flags field. Now, for most standard branches, the flags happens to be 2C36. Don't know what it means, once again, and you'll get a lot of entries that aren't this, but these are the only ones I track. So once again, just for reference, this is what code looks like to actually parse this structure. We're not really going to look into it. It's just you loop through, check if the flags match, and then save off that you hit a PC. So this is the CMU paper that actually references this. I was able to kind of get everything working based on this paper. They don't really go through every single detail on how to set it up, but I think they do mention the magic number, which is where I found it. So if anyone wants to look this up, that's what it is called. Next, we're going to talk about Intel's branch trace store. It's pretty much the same thing as AMD's undocumented feature, except it's documented and on Intel. It has the same problems where it's pretty slow and it destroys memory bandwidth. And there's really nothing much more different about it other than the fact that you can filter based on the privilege level. So you can filter out kernel events if you only want to look at userland or vice versa. The next feature is Intel's processor trace. They call it PT. It's been around, I think, in theory for a couple years now, but it's only actually been in silicon for a year or two. It is a compressed stream similar to BTS, where you're going to get all the traces out of a system, but now it's compressed. For example, a packet for a conditional branch is only going to encode 1 bit, and that bit's going to tell you whether or not the branch was taken or not taken. Due to this fact, you actually have to post-process all the results from this trace to try and determine what those branches were and where they were going. So indirect jumps you'll get a full value for, but for the standard jumps and for the conditional branches, you're going to have to decode that after the fact, which makes this a little bit harder to use. Other downsides is it's very new, so you need a very new recent processor, and the early implementations of it in silicon also didn't work in VTX mode. I actually don't have any processors that can use this, such that I'm not able to really judge how well it works versus how well it doesn't work. I have to go by other people's reference. So now we have a technique that I started doing about 3 months ago, and it's one of my favorite ones out there. So is anyone familiar with performance counters on system, the RDPMC instruction? So basically, on Intel and AMD, you have a bunch of different performance events that you can trace. And these are going to be things that a developer would want to know to try and figure out what's going on in their application. Why is it going slow? So it will tell you, like, if you have a lot of instruction cache misses or data cache misses, the state of your TLBs, all sorts of different events that you can say, hey, increment a counter every time this occurs. And then after the fact, I can look at those counters and determine where there were slowdowns. What's nice about this is that there are a bunch of very interesting counters, and you are able to have an interrupt fire if there's an overflow of a counter. So if an event comes in and overflows the counter, you'll get an interrupt, and now you know, hey, I need to reset this counter and keep track that it overflowed. But what's convenient is you can actually set the count yourself. So you can set it to be 1 less than the maximum for a performance counter, and now on the next event, you're going to get an interrupt. So basically, anything that a performance counter can count, any event that it can count, you can get an interrupt on. Downsides are this is not a synchronous event. So if you say, hey, I want an interrupt on the next dcache miss, you might actually get an interrupt a few instructions after that miss occurs. They aren't guaranteed to be synchronous, and you can get multiple events in one interrupt, and it can be confusing. But one thing that I particularly look at is the event that's present on AMD systems, and I think there's an Intel equivalent, which is instruction cache refills from L3 cache or system memory. And basically, to me, what this is saying is, hey, you just executed some code that hasn't been in the most recent chunks of code. It's all the way out in L3, it's all the way out in system memory. And what's cool is once you've actually executed that instruction, you're no longer going to get these events. So it's self-silencing. It will tell you, hey, you hit new code, and then after that, it no longer is telling you on these things that you might not care about anymore. So I've kind of already mentioned some of the pros and cons of it. You can filter on CPL. You can have it only work if you're in a VM guest or you're not in a guest. So you can kind of filter on what environment you're actually running in. But we kind of already covered the pros and cons in the previous slide. So the next thing is page fault coverage. This one's pretty simple. It's also really crude. You can just start paging out pages, and then when someone tries to access them, you'll know if it's a read-write or an execute access, and you can kind of decide whether or not you want to store that information. It's a way of doing coverage, but it's not really something I recommend. It's really crude. It's kind of ugly, but it's simple to set up quickly. Finally, we're going to talk about something that I actually haven't implemented yet. I've only thought of, but it is execute no read with breakpoints. So on Intel systems and Intel only, you can have executable and non-readable pages, meaning that you can have your code basically be invisible to any data accesses while it can still be executing under the hood. What's neat about this is that I can mark all the memory of a system as executable and not readable, such that then I can fill in all of the code with CCs, which are breakpoints on x86. And then once I've gotten a breakpoint, I'm able to fill in one instruction. So replace the CCs with one instruction from whatever the original contents of the page was. And now it'll break on the next one. And I keep doing this over and over and over again. So initially it will be very slow, but slowly it's kind of like a scratch-off ticket. You scratch it off and more and more and more becomes revealed, and eventually you stop getting these events. So some downsides are that you only get binary information. You only know whether or not you've hit it once, because after you've filled it in, you're no longer going to get events. But the important part about execute no read is that since you're changing the underlying data from what it originally was to now these CCs, you're able to get a page fault when someone actually tries to read or write to it. And once someone reads or writes to it, you can actually replace it with the original page. So you're going to lose tracking on a page that you restore, but you also won't have any corrupt reads or writes that are now working with invalid data. So once again, I haven't actually tried it yet, and I'm excited to do it. Kind of already covered the pros and cons on this one as well. There's no pre-processing, static analysis. You don't have to know where all the code is. This will kind of figure it out for you. So this is just a summary of all the different features of all the different mechanisms. Don't really have to go through this because we went through it on each slide, but it's there for reference when the slide decks go around. So now we're going to talk about using coverage. So once again, this is kind of my standard graph. On this one, on the x-axis, I have the number of fuzz cases. And on the y-axis, I have the number of unique PCs I've hit in a run. So this green line here, I think it's green, I'm pretty colorblind, is a run without any coverage at all, or without any coverage feedback. So I'm still capturing the coverage because I'm able to display these graphs, but I'm not actually feeding anything back. Now this is on a protocol, it was a binary protocol that I had no information on what it was. I was just generating a random stream of bits, and so on this green line on the bottom here, all I was doing is feeding in random bits each time over and over again. Now on these three lines on the top, I did a different method of code coverage feedback, such that I would have an interesting case that would hit a new PC that I've never hit before. I'd save that input off, and then I'd feed that back in and mutate it just a little bit to see if I could get more code out of it. So one thing that's important to note is that this is a log scale graph, like all the graphs I look at. So this is about 100 times ahead of what the other one was. So you don't get 100 times more coverage, but you do get to where the coverage was 100 times faster. So when do you want to actually gather code coverage information? And as I've been going through all the slides, you've seen a lot of these cost a lot of time. They can be, hundreds of times slowdown or a 50 times slowdown, unless it costs something to gather this information. So one thing to note is that you don't always want to gather this information. A common case is if you have a really good generator, you can generate a really good PDF, but you can't mutate that PDF. Then you don't really gain anything by saving off a good PDF and then mutating it with your bad mutator. You're better off just using your generator to generate more PDFs faster, and you're not paying the cost. So, of course, like all of this stuff, a lot of it comes down to what works for you. And it's hard to usually tell. You just have to kind of try out these methods and see which one's giving you interesting information. So another thing that's nice about gathering code coverage information is you can tell when your fuzzer is improving or when you are hitting new code. And like I kind of mentioned before, you might not be getting crashes, so you don't really have a foothold in what's occurring, but you can look at the coverage information to try and determine, have you hit more code? Have you done something? And one thing to note is that more coverage is not always better. You could have something that is just looking broad and it's just hitting everything just a tiny bit deep, but a lot of different things. And you might have a lot of coverage, but you're not focusing on anything hard enough to find a bug. So it's not always something you want to spend all your time on. There are some people getting so wrapped up in coverage, and start to forget it's more about depth than coverage. But usually they're correlated. So now we're going to talk about how do you deal with slow coverage. So all of these techniques have some sort of cost, and the really good ones like single stepping that give you all the information you possibly want have 300 times slowdowns. So how do you deal with them? So one way is you just take faster lossy mechanisms like the interrupt-based sampling or the performance counter stuff, and you have that feed into some sort of a queue that says, hey, I found something interesting in this one input. Can you run it through and do single stepping through the whole input to try and find if there's more information? Because you could randomly sample one new block and say, hey, I found a new block with this input. But little did you know there are thousands of new blocks up to that point that you didn't know you hit in that run. So it's always important to try and figure that out. Another thing is that you can try and combine the coverage information with some symbolic sort of execution. If you have all of this information telling you what register state was, what memory state is, you could potentially feed this into something that's doing symbolic analysis to try and solve for a branch. And while it might have been 100 times slowdown to gather that information, the solver could have given you 100 times speed up in finding a branch that you would have had to throw millions of cases at to ever actually go through. So another thing that's important to mention is throttling. So now you're dealing with all of this information coming in, all of these traces. Now, at some point, you might have too much data coming in. You might be dealing with so much that you're not able to actually analyze anything that you've processed. So there's a ratio that I always like to look at. It's this fuzz cases to fuzz input ratio. So basically, how many fuzz cases have I done? And then how many unique fuzz inputs have I saved off in the database? I hit new coverage, so I saved off that input. And if this number is really low, like 2, that means you've only explored each input twice, which doesn't mean it means you haven't put much time into each input, and thus, how do you know you've really actually expanded on the previous knowledge of your input base? So what I normally do is I pick an arbitrary number, let's say 100, for the fuzz cases to fuzz input ratio, meaning I want 100 different fuzz cases for every single input I have in my database. And at that point in time, I start to realize I'm not really gaining anything more, so I need to find more information on the system. So this is where I turn up the throttle and turn on something like register or memory coverage. So once you become starved of information, you're not gaining anything by the CPU cycles if you're not saving any of the inputs. So if you run for an hour and don't save off any new inputs, that entire hour of time has been wasted. So next is using coverage information. How do you actually end up using it? So one way is if you have a generator and your generator takes a bunch of parameters, you can save off the parameters that caused you to generate whatever output it was that hit your new state or a crash or whatever it was. Similarly, you can just save off the original input. If you generated a PDF, you can just save off the actual PDF and then feed it back through with some mutations. So one thing that's important is that you can use the memory or register information to try and determine when parts of your file were loaded or what part of the file you were in when you hit this new coverage. And then when you're feeding it back in, you can try and mutate it locally to where the code coverage changed. If you have a 512 kilobyte input file, it's usually not much good to mutate some random bytes in it because you're not actually mutating near to what caused you to hit the new code. Other things like I mentioned already, so you can colorize IDA and give this information to someone doing source analysis. The other thing that I really like to do is to have a database of all these inputs. So I have all these hashes of what has caused me to hit all of these different coverage cases. So when I'm looking through source code, I'm able to see, oh, this looks like a function that could potentially have a bug. How close have I gotten? And I can see an input that can already get me close to there, so I don't have to spend the rest of the weekend trying to actually get to that code. I can already get maybe within a function or two, or ideally, be right at an if statement. So, like I said, I want to talk about what I kind of already do right now. After all of this work, what have I myself found myself doing? And I'm using the L1 instruction cache performance counters, like I mentioned. That's like my first tier. I have that running on all cores all the time. It's about a 2.5 times slowdown. So to me, 2.5 times doesn't really matter. It's like a rounding error in the number of fuzz cases you're getting. Then I use this to feed into a queue like I mentioned before. And then this will eventually, it will go into the AMD BH trace information such that I can get the full trace out of each input. And if that full trace looks interesting, then I'll actually single step the entire input. The other things is I do a lot of static analysis. I like to color all of my IDA scripts or IDA databases such that I'm able to look around at what I've hit. You'll see a branch that your fuzzer can't solve, but when you look at it, it's just doing a compare against some magic 64-bit number. You're never going to randomly generate it, but as a human, you can go and zap that in right away. I also do crash feedback, so not only do I do code feedback, when I actually get a crash, I'll save that off and feed it back a lot as well and just mutate it similar to code coverage. And then also I'll store all the unique inputs somewhere over a network such that I can use them in future runs or use them for static analysis later, similar to like the comments in C code. So I have to check the time on this one depending on like how much I'm over or under, whether I can go into these graphs. It looks like I have a little bit of time. So I have a few graphs that I generate, and I'll kind of show you what my standard working environment is. So I have this graph, and it should be, not that one. I have this one. So this is kind of the standard output that I usually look at when I'm actually running a fuzz case. It's a little bit scrunched because I'm not used to being on a projector. But basically, every single graph will have the exact same x-axis. In this case, it's time elapsed in seconds. And then the y-axis is the only thing changing on all the graphs. And similarly, all the graphs are log scale and the exact same x-axis. So up in the top left, I have the code coverage. This is going to tell me how many edges or PCs or whatever I happen to be tracing at the time that I've hit. I then have the fuzz cases per second. This is what I'm keeping an eye on to try and figure out how quickly I'm going. In the top right, I have the number of unique crashes, because of course that's what all of this is about, is trying to get more crashes. I have the number of inputs, so this tells me how many inputs are in my database. This yellow line is kind of an anomaly, and that is due to the performance counter, or really any interrupt-based sampling, which is going to cause you to sample a lot of random things in each binary, and thus you create so many inputs kind of for no reason. I also have this fuzzes per input. This is kind of the threshold that I look at to try and determine if I should turn on new mechanisms or not. I have the coverage per input, which is actually a graph I don't use too much. It's just how much am I gaining from each input. I have the efficiency, which is how much time I spend in the host and how much time I spend in the guest. Basically, I want to spend all my time in the VM because that's when the actual target code is running. And then I have VM exits per second. So VM exits are how you actually exit out of a VM if there's an interrupt or something. And these are very expensive. They're about 400 to 500 cycles, such that I really want to keep an eye on these. So this line up here is single stepping. So as you can see, I'm exiting the VM about 1 million times every single time I execute or run a fuzz case. And then finally, I just have number of crashes. Once again, kind of a useless graph because I do crash feedback, such that once you get one crash, it's going to look like you have a bunch because you keep feeding the same input back through. But to kind of blow up some of these charts, the main one that's interesting is the coverage graph. And basically, this in this graph, I have on the X scale, no longer in seconds, but this is in number of fuzz cases. Can everyone read this pretty well? I sadly can't do much to like make it better to read because it's a new plot and it's kind of bad. But basically, this is 5 different methods that I'm, actually 6 different methods that I'm plotting here. I have single stepping on here. I have branch single stepping. I have the AMD BH trace control stuff. I have no coverage, which is just a baseline. And then I also have the BH trace control only turned on 8 cores. I have a 64-core system, so it's only on 12% of the cores, so it kind of cuts down. So all 3 lines here, you're going to have your branch single stepping, your single stepping, and the AMD trace always on. And the reason these all are pretty much identical, and in theory they should be identical, the only reason they differ is because each time I run my fuzzer, I have a different random seed, so they will randomly find code sooner or later. But essentially, all of these are giving the baseline for perfect coverage in a run. This yellow or orange or green line here is what happens when you have the performance counters going. So this is when you have performance counters always going every single time you have an L1I fetch from an L3 or system memory. So you can see that one's lagging behind by quite a bit. Once again, it's log scale, so that's about 100 times slowdown. And then this final line here is what happens when you have the BH trace control only on a certain percentage of the time or a certain number of cores. So you can see it's definitely hindered in terms of how much you're getting out of it. But what's interesting is that this graph is in number of fuzz cases, not amount of time. So this graph is not taking into account how expensive single stepping is. So that's why, with a little bit of a quick modification of a script here, I can change the time scale, which I probably just should have generated these graphs, but all right, sorry. And now we have this in time scale. And as you'll see, what we had before is all three of the single stepping, the branch single stepping, and the AMD tracing were all at the top before. But now that's no longer the case. The AMD trace control is by far winning. It is the best ratio of amount of coverage you're getting out of it versus the amount of time it actually costs to compute it. The RDPMC is very similar here, or the performance counter stuff is very similar once again. You have the branch single stepping. It's once again lagging quite a bit behind the AMD stuff. I feel like a weatherman right now. Then we have, let's see, I can't tell these colors. This is single step here. So while it looked like single step was great in the previous one, when it's actually in the time domain, it's pretty awful because it costs so much to run, which by process of elimination leaves this final line here to be the branch. This is the branch control only on 8 cores of the system. So the other thing to look at is one more graph that will blow up. What's that?
Why is branch control on 8 cores slower than branch control on every core?
Yeah, because you miss a lot of the things, that are actually being covered. And then I also have the fuzz cases per second, and this one's just going to kind of show how fast these things are running. So it kind of changes over time. So one thing with feedback that's very interesting is even if you're not actually slowing things down due to gathering the code coverage information, things will naturally slow down because usually when you favor unique code, you're going to favor deeper paths, which means you're going to get like weird shapes in your graph where like in this period of time I was exploring really deep into code and thus I was getting fewer cases. So this very top line here, once again, no idea what color it is. That is with absolutely no feedback at all, or with no collection of any of the coverage information. So that's why it's on the top. It's the fastest, and it should always be the fastest because there's no overhead. This next line is the BH trace control on only 8 of the cores. Since I'm only running on 12% of the cores, even if those 12% of cores went completely offline and did no coverage at all, it would only be a little bit of a performance slowdown of 12%. The yellow line here, once again, is the performance counter stuff. And then at the very bottom, we have the slower ones. So these are going to be our, on top here, we have the BH trace control, which is about 40 fuzz cases a second in this case. Then we have the branch single stepping here at about 20 fuzz cases a second. And then at about 4 fuzz cases per second, we have the actual single stepping, which is very slow. So we can jump back into the presentation here. And the conclusion, one thing that I really want everyone to take out of this is code coverage is not always needed. Don't focus so much on always gathering code coverage information. It might just be slowing you down. So I always recommend run your code without code coverage and run your code with code coverage and see which one is yielding more crashes or more information. It's difficult to try and determine if you're doing better or not if you don't have any crashes without gathering the code coverage information, but you can always gather cheap code coverage information. You can always get something that's maybe not accurate, but you can use it relatively to compare with other runs. The other thing is slow methods can be used part-time. You don't have to always use a fast method. You can use a slow method and only use it 1% of the time, and now it's not very expensive anymore. And then finally, coverage should always be evaluated on a per case basis. And this is kind of what I already was mentioning at the top of this slide. So next, any questions? Does anyone have any questions? I've been screaming at you this whole time. And it's a lot of weird OS level technical documentation. And I want to make sure everyone can get something out of this presentation. So any questions?
You have to repeat the question and you get it asked for the mic.
What? Oh, okay. Yeah. Any questions?
When you're randomly sampling,
Mm-hmm.
how many times do you rerun the same file to get like, or do you rerun each test case a whole bunch of times to see how much coverage you actually got, or do you just like?
Okay.
That's not really
Yeah.
a question, but I hope I said enough things.
So from what I'm getting, I think the question is, when I'm doing something that is not giving me perfect coverage information, do I run it through until it becomes perfect or it gets near perfect? Like, do I run it multiple times? The answer is no. I just deal with the fact that I'm losing information, and hopefully I'll pick it up later to do deeper introspection. So when I initially started out, when I was doing all the inart-based sampling, I would have graphs that were very inaccurate. They had like maybe only a fourth of the code that I actually had documented, but it was cheap. I'd answer it?
Yeah.
Cool. Any other questions?
I want to learn more about Fulkvisor. Where should I go online?
Okay, so someone wants to learn more about Fulkvisor. There happens to be, I think it might show up if you Google it, there's like a 3.5-hour video on YouTube of me just talking to my screen. Kind of similar stuff where I just get really excited and go off on tangents, but it's a little less filtered, and I'm trying to do those every once in a while, like a live stream. But I think also I made one tweet, and there's something on a paste bin somewhere too. But no, it is not.
Inside facebook.com. Not.
Yes. You can also contact me. I'm usually a pretty friendly person. I have my phone on me at all times, and I probably will answer your email within a couple hours, especially if it's outside of human hours, because I don't believe in mornings. Got a question here?
Sure. Have you ever used this to detect algorithms? So, like, for instance, a fast-forward transform algorithm on a particular processor?
Okay. The question was, do I ever use this to try and determine if there are any algorithms running on a system, like a fast Fourier transform or something like that? I actually haven't. I haven't used this to try and determine what type of code is running. I only use it to determine if code is running or not. And usually it will come down to static analysis. But I do think there's a lot of merit to trying to detect like patterns in how code is flowing to try and determine, is an algorithm here, or you could probably even use it to determine certain types of crypto of like how are things being implemented, what instructions are being used in what sequences. So.
For some of the heavier methods, like tracking changes in registers, changes in memory, do you have like a rough order of magnitude for the size of the logs that generates?
So usually my input database like peaks out at like 50 gigabytes once I've kind of run out of things to do code coverage on. And then once I turn on register and memory coverage, it usually grows to like half a terabyte to a terabyte. And very quickly. So what I actually do is I will, every time I run, I'll check the 100 threshold. So I kind of get this wavy pattern. So I actually don't have a graph for it, but it will be like climbing up to 100, and then it will stay at 100 pretty much permanently. And once it's no longer pinned at 100, it's kind of an interesting case, because it means I'm failing to find any unique new information. So yeah, it's definitely very expensive. I'd say on average, it's probably 50 to 100 times more information than standard, depending on how much you store for register and memory information.
Can you talk a little bit about what you're doing to analyze that massive pile of data, or how the feedback system works?
Okay, so the question, or what was asked is, how do I actually deal with this massive pile of information? How do I feed it back? So similar to kind of what I've said, a lot of times I will have a different fuzzer for different targets, and some are generative, some are mutational. But when I have a mutational fuzzer, it's very convenient because all I do is I save off the inputs that cause me to hit those paths, and then I mutate them a little bit and feed them back through. As a human, I don't really analyze the inputs. I usually will only look at the IDA graph and try and determine like, what I've hit, what is interesting, and then try and determine the inputs that got me to interesting places. So there's a lot to do there. We were kind of brainstorming earlier. There are interesting things where if you mutate a previous input, you could potentially, if you keep track of where your parent was, like what you were mutating from, you can increment a count on your parent and kind of keep track of what sources are creating new trees of like very interesting inputs. So you'll have like a few inputs at the top, and each one of those have been mutated, and they're kind of trickling up and telling everyone like, hey, my parent was really good, maybe you should do another fork of the parent. So there are a lot of things to do with this information, and I definitely haven't even scratched the surface on what to actually look at. So, any other questions? All right, sounds good.